So in this video, we are going to discuss the Gaussian integral that we used in our main lecture. So of course, the Gaussian integral is one of the most fundamental integrals that's used quite often in physics. And I'm sure you all know the fundamental Gaussian integral. So in this lecture, what we're going to do is that we're just going to discuss how the result of the Gaussian integral is going to be rearranged to give some physical meaning to the wave function that we saw in the lecture. So the wave function that we were dealing with had up to some heaviside theta function, had a form like this. It had a normalization which had lambda squared by 4 pi cubed, and this was raised to the power 1/4. And then inside the integral, this was an integral that was a dk1 integral, and inside it there was this factor which came from the time dependence of the energy. So that was k1 squared by 2m of t. And then we had a Gaussian part, which is k minus k0 squared del squared by 2. And then we had these two factors. So to do this integral, we are going to use the Gaussian integral identity, which I'm assuming you all know how to derive. If you don't, then you have to look up how to derive this. So if you're doing this course and you don't know how to derive this identity, then you need to go back and derive this identity. Learn how to derive this. If you have problems, please get in touch with me and I will show you. So this is the result that we are going to use. So to use this, we will rewrite the integral I in the following way. So I will have the normalization and inside the integral, what we will do is that we will rearrange everything so that the argument of the exponent has this form. So we get first the coefficient of k1 squared. So we have, say, del squared by 2 plus I h bar t by 2m, and then k1 squared. And then we have the coefficient of k, or k1, and that's going to have k0 del squared plus iy k1, and then a factor which does not depend on k1. So this factor, of course, we can pull out of the integral. So let's do that. So we have our normalization, and then this factor is pulled out. And then the rest of it, we use the Gaussian integral that we showed here. So this is alpha and this is beta. So we use this, so then we write e to the power, what is it? It should be beta squared by 4 alpha. So beta squared is going to be k0 delta squared plus iy whole squared. Then there's 4, and alpha is going to be del squared by 2 plus I h bar t over 2m. And then we're going to have the factor of square root of pi over alpha. So we multiply this with pi to the power half divided by del squared by 2 plus I h bar t by 2m, and this whole thing is under square root. Right. So then what we do is that we simplify things. First, we simplify the normalization constant. So we have del squared by 4 pi cubed, and this is to the power 1/4. And then we see here we have a factor of square root of pi. So if I write this factor of square root of pi inside a bracket which is raised to the power 1/4, then it's just going to be pi squared, because 1/4 times 2 is half. So because of that, we get 1/4. And then what we do is that we factor out one factor of delta. So just one factor of delta and half from the square root. And when we pull it out here, what we get is that this factor of half, which was in the bottom of the denominator or in the denominator of the denominator, will come to the numerator here, and this will become 4. Because there's a square root here and there's a 1/4 here. And the one factor of delta that we pulled out will become delta squared. So if I do this, then you can see that this factor of 4 will cancel out this factor of 4. This del squared will cancel out with this del squared. This pi squared will cancel out with pi squared here, leaving behind one factor of pi in under the power 1/4. Okay, so this takes care of the constant. And then we have the time dependent factor, which is this factor, because we have factored out delta, one factor of delta and half. This thing becomes, so it becomes delta plus I h bar t by m delta. And we are writing it in the numerator, but we're putting a power of minus half. Okay, that takes care of all the normalization type constant, but then we have also this other factor. We have this factor, and that factor is just e to the power minus k naught squared del squared by 2, and then we have the exponential factor k naught, the other exponential factor. Sorry, this should be y, and then divided by 4 alpha. Right. So now what we're going to do is that we're going to simplify the argument of the exponential. So the argument of the exponentials is given by, so first, k naught squared, the del squared by 2, and then we have k naught del squared plus iy whole squared divided by 2 del squared 1 plus I h bar t m del squared. We have factored out del squared and half from this thing. So that's how we get this guy. So after we have written this, we can expand the whole square and then add these two terms. So if I do that, then of course in the denominator, I'm going to get 2 del squared 1 plus I h bar t by m delta squared. And then in the numerator, the first term is going to be k squared del squared, because it has a factor of 2 here. Only this guy will be multiplying this. So we get, so as a result, we get another del squared, so that del squared becomes del to the power 4th, and then we have 1 plus I h bar t over m del squared plus, now we are expanding the whole squared, so we have k squared del to the power 4 minus y squared, because there's an I, and then we have plus 2i y k naught delta squared. Now we see that this thing and this thing, this thing and the first term here, they cancel out. So as a result, so we are going to write this as, so let's just write the numerator now. So the numerator of this thing. So what is the numerator? The numerator has minus I h bar t k naught squared, and then del squared by m, because of the cancellation between del to the power 4th and del squared here. And then we have minus y squared, and then we have plus 2i y k naught del squared. So, and then what we're going to do is that we're going to rearrange these terms. So we're going to write minus y squared first, and then we are going to subtract this term, which wasn't there before. So it's a real term. And then we're going to add another term, which also wasn't there, which is 2y h bar k naught t by m. And then we're going to write the terms which were already there. So first we write, okay, so then what we do is that we write this guy. So this is going to be plus 2iy k naught del squared. And then what we're going to do is that, we added this term. We're now going to subtract this term. So if you subtract this term, we get minus 2y h bar k0 t by m. And then what we'll do is that we'll write this other term, and this other term is going to be minus I h bar t k naught squared del squared by m. And then remember that we subtracted this term, so we have to add this term. So we have to add this term, so we have here h squared k naught squared t squared m squared. All right. So when we have added this term, the first three terms, they combine to give me y minus h bar k naught t by m whole squared. And then this term and this term, we see that we can take a bunch of stuff common from there, and we can factor out k0 and y. And if we do this, we get in the bracket 2 delta squared plus I squared 2 h bar t over m. And then in the last two term, we can factor out, again, a bunch of stuff. So if we factor out I h bar k naught squared t over 2m, we get exactly the same thing as the term before in the brackets, 2i squared sorry, we don't get a 2i squared. I made a mistake. This was just I times 2, and here it's just I times 2, right? So then we have 2i h bar t over m. So we have exactly these two terms. So, and then what we do is that, okay, we rewrite this as minus y minus h bar k0 t over m whole squared plus I k0 y minus I h bar k0 squared t by 2m times 2 del squared plus, say, 2I h bar t over m. So now if I look at the whole argument of the exponential, so see that the exponential argument had this 2 del squared 1 plus I h bar t by m delta squared common, and we can see that in the right. So yeah, we see that that will cancel out this guy, right? Because if I take 2 delta squared common from this, I just get exactly this thing. So we can write the argument again, the argument of the exponential to be, say, minus y minus h bar k0 t over m whole squared divided by 2 del squared 1 plus I h bar t over m del squared. So this is the first term. And the second term, we're just going to get, say, I k naught. And then inside the bracket, we will get y minus I h naught k0 k0 by 2m. Yeah, right. So now if I go back to my integral is going to be I, and what I've done is that I've actually set y equals to x plus a, so we can now substitute that back in, because we in the original integral in the lecture we had x plus a, but we could replace it by y. So when we do that, then I get pi to the power minus 1/4 del plus I h bar t by m delta to the power minus 1/2, and then I get e to the power minus x plus a minus h bar k0 t over m whole squared divided by 2 delta squared 1 plus I h bar t by m delta squared times e to the power I k0 x plus a minus h bar k0 t by 2m. So let's discuss what it is. So this is just a normalization, and this is a normalization which is time dependent. And as time increases, this factor increases, but it has a negative power, and therefore this factor would be decreasing. So what it means is that as time goes on, the height of the Gaussian is, the amplitude is decreasing. Whereas this is the Gaussian factor, and what it is saying is that the position of the Gaussian is minus a plus this factor, which depends on time. So as time goes on, for large values of t, this we can ignore this a. So for large values of t, the position of the Gaussian is going to be given by h bar k naught t over m. So it'll be in the positive x-axis. And then what this means is that the width of the Gaussian is also time dependent, and the width increases with time. So that Gaussian not only just like it decreases in its amplitude, it also spreads out. So if you were to draw a picture, the initial Gaussian is something like this, but as it moves, it spreads out, and the height, the amplitude is also decreasing. So this is, of course, the width, and this is the height. And this one is just telling you what the momentum information is.